Hello, my name is Camden Beauchart, and today I will be going through our senior project, which includes my team members Jonah, Matt, and Drew, and is sponsored by one of our own Cal Poly professors, Andrew Keene. So, to describe a bit about our project, let's first take a look at the need our project is hoping to solve. For mountain bike riders, any bike that is designed with a slack head tube angle creates a force phenomenon commonly referred to as fork flop that occurs whenever a rider is ascending a steep hill or is pedaling at low speeds. An extreme example of this can be seen in the photo shown here with an old bike that used to be on campus. So the need for our project is to somehow create a device using internal springs that can improve the response of the bike that has a slack head tube angle. For our design process, we went through many ideation sessions to allow for a multitude of solutions to be brainstormed before locking onto just one idea. Our team landed on an original design that would interact with the bike head tube and house two torsion springs to provide the counteracting forces on the bike. After presenting this design at our preliminary design review, we got crucial feedback from both our peers and our sponsor to tweak parts of our design to make it more secure and to simplify the way that it attaches to the bike. Following this, we simplified the design and created a spacer design that would sit in the place of a typical bike spacer and house our torsion springs, which then interact with a separate piece that is connected to the bike frame. While landing on this newer design, we were still constantly tweaking and editing small components on the spacer and the housing, as we found new issues that might hinder the way this design performs, such as a rider hitting the housing with their leg, or the spacer design not allowing for full rotation of the springs. These edits in our design led us to the design you can see pictured here, with two separate spacers, two clamps around the head tube, and a housing for the springs to interact with the pin. Taking this design into our critical design review, we again received valuable feedback that made us rethink some of our design. So for our final design, Jonah will give a quick overview of all the components.
This is our final design. It uses two torsion springs that counteract unwanted steering moments about the steering axis. These springs are fixed to the bike using custom spacers. Our design also makes use of a clamp attached to a housing, which interacts with the spring legs in order to provide the necessary spring forces. The following videos and animations show how this works.
We sized our torsion springs based on the forces we expect fork flop to create on the bike we used for testing. We took given spring constant values from suppliers' websites and then used various statics equations to determine what force and moment arm would create the correct restorative force on the bike. On top of ensuring the spring forces were correct, we also conducted FEA studies on the spacer design to determine the forces the spacers would experience while in compression on the bike. This allowed us to see that our components would not fail under the stresses the bike places on the spacer system. Once we had manufactured our prototype, we began our testing process with a quick test to ensure that we could begin our true design verification. This test was to make sure the fitment of the prototype was correct, and that all components could fit on the bike to allow for later testing. Once we had our device on the bike, we gave the handlebars a quick turn to ensure that our springs were indeed counteracting the flop of the fork. And now, Drew will describe how we began our design verification testing.
Our project had 9 engineering specifications that guided our design. The primary specification we were tasked with satisfying was decreasing the fork flop moment when the device was installed. We also had to maintain 80% of the optimal function while under elevated heat and normal riding conditions such as in rain and mud. Our design must also be able to be installed in under 20 minutes, adjusted in less than 60 seconds, weigh less than 20 pounds, have a volume of less than 53 cubic inches, and score at least a 75% satisfaction rating in user feedback and aesthetics.
Fork flop is a difficult phenomenon to measure, and therefore moments about the steering axis were measured instead. Since fork flop is essentially a moment about the steering axis, we felt this was a good compromise and would still provide a lot of insight into how the device was performing. Multiple tests were conducted with the device at its maximum setting, meaning the springs were providing the most possible resistance. To measure the moments about the steering axis, a simple fixture was designed to fit load cells in and allow the rider to still provide steering inputs into the bike. This test was essentially a proof by comparison, in which target data from the safety bike was compared with the test bike. Maximums and averages were calculated as well in order to get a more global perspective of the results.
As a result of testing the moment applied by the rider in response to the fork flop, we found a peak moment of close to 100 pound-force inches. After installing the device on the bike, we saw nearly a 40% reduction in steering moment applied by the rider, providing evidence for successful improvement in fork flop and rider stability.
And in conclusion, our design performed closely to what we expected and taught us numerous lessons concerning the importance of manufacturability of parts and the ability to adapt to new issues that arise. And finally, our team would like to thank our sponsor, Dr. Keene, for the continued support throughout the project, as well as thank Meredith Rubin, who allowed us to purchase components for our design through our provided budget. And thank you all for your time.